Welcome if you have joined already. Feel free to say hi in the chat so I know you're here. So we're just kicking it off. I think we're just live now. And we're going to be looking at chain rule today, which is part of year 13 differentiation. So a really important topic, quite a big, challenging, involved one. I'm just checking the chat to see who we've got. Welcome if you've just joined. And as I said, feel free to say hi. I hope everyone's keeping well. And, you know, we're kind of plodding on, carrying on with this kind of strange year still, and kind of phasing back into normality at school and stuff. Hi, excellent, lovely. I can see lots of people involved already. That's great. It's a bit of an evening one, especially when it's darker at this time now. So I know, well done for all getting here on a Sunday. And this is a big full-on topic. So it might be something you've started already. Let me know in the chat as well if you've done differentiation and if you've done specifically the chain rule. So I've got an idea of if this is revision or if this is actually brand new to you. It is quite a tricky topic, but we're going to go through and get as far as we can with it. So good. Lovely. Right, so some people are actually on it at the moment. Cool. So what I'm going to do is share my screen and we can start running through some content now. So here we go. Hopefully everyone can see my PowerPoint, the slides and everything. I'll make that nice and full screen and just let me know in the chat you can see that. It looks like that's all shared. Well done. Cool. So just to start with, I'll give a quick introduction to what we're doing and SnapRevise. So I'm Max, I'm head of maths at SnapRevise, and I did my degree in maths and have been teaching A-level and below ever since really, and have done a lot of web classes for SnapRevise and building and working through the A-level content. So I'm going to run through some kind of key things we do and then look at some differentiation today. Just to bear in mind that if you follow us on Instagram and take a picture of the web class, share it to your story and tag SnapRevise, we're giving away a free account for one. And there is also going to be a coupon code at the end for a discount for SnapRevise. So stay tuned for that. And obviously keep active in the chat with asking any questions, asking me to go over anything if you're unsure, because this is, as I said, differentiation, a big topic, and also comes up again when we hit integration later on in the course. Brilliant. Right, it's good to see so many of you here, and I'm sure you're keen to get started on this, so we'll get cracking. So to begin with, what we're going to look at today, we're going to look at how to differentiate with brackets raised to powers. So this is a much more involved process than you would have seen in year 12, and this is essentially the chain rule, even if we have negative and fractional powers for a bracket. So we're going to look at that today. Welcome to anyone new and anyone that's said hello. Sorry if I've missed you. So this is a really key idea we're going to look at, and it's called the chain rule. So we're going to also look at applying it to simple trig and exponential functions as well. I'm not going to do differentiation from first principles. That's not what this is covering, and it's not covering graph sketching. It's this specific rule called the chain rule that we're going to look at. Okay, so I'm going to carry on and get started, and I'm just going to go through some things that will be kind of prerequisite knowledge for this. So this should be largely a recap. So x to the power of n, if you know what that differentiates to, let me know in the chat. But in general terms, that will just be nx to the n minus 1. So basically year 12 style, you essentially, yeah, absolutely, times by the power, drop the power by 1. Brilliant. The other thing to remember is that differentiation is like a linear operation, and so it's not affected by scalars and additions. You just differentiate each bit separately. So the next bit will become n alpha x to the n minus 1, and then plus m beta x to the m minus 1. So I'm just doing this very much in general terms. This is year 13. This is just a quick recap of things you know from year 12 before we get on to the newer ideas. So if this is easy, then that's good. It's just a recap to start with. So just quickly reminding ourselves how to do these different things from differentiation. I would rewrite this as x to the power as 1 over n. and x to the power of minus m. And then differentiating that, we're going to get, and feel free to do it ahead of me and check you agree. Okay. Superb. Right, so in year 12, you might not have done much differentiation yet, but this is a key part of a bigger topic we call calculus, and it's used for finding gradient functions. So this sort of part of it is the year 12 style knowledge, and you'll also do a topic called exponentials. And when we differentiate exponentials, it actually becomes the same thing. So they're quite nice. Trig differentiation is actually more kind of a thing we explore in year 13. If you know how to do that, let me know. Absolutely, sine differentiates to cos. So a number times sine differentiates to that same number times cos. And cos differentiates to minus sine. So we're just doing it very much in general terms. Brilliant, well done, cool. So moving it on, we're going to just quickly have a look at some year 12 recap that's going to tie in and basically come to grips with the chain rule for year 13. So next slide we're going to just look at is here. Right, so all the examples, AQA, EdXL, OCR, all pretty much cover the exact same thing in terms of differentiation. It's pretty much consistent across all the boards, and that's the same with a lot of the A-level maths content now. And so since 2017, since the A-levels kind of reformed a bit more, there's been a lot of tightening up so that the exam boards don't differ too much. But this has always been a topic on the A-level, so there's loads of resources on this to practice with. Here we go. So if we differentiate the following, to do it in a sort of year 12 style, let's first actually expand that double bracket. Okay, so we're essentially differentiating x squared plus 6x plus 9. And remember we said we times by the power, drop the power by 1. So year 12 style, what does that differentiate to? It differentiates to 2x plus 6. Now what I'm going to do is just write that in a slightly different way. I'm going to write it in a factorized form, 2 times x plus 3. And we'll see why I'm doing that in a minute. So that's hopefully not too bad. The next one, I'm going to differentiate again by expanding it, although it is a little bit more tedious expanding a triple bracket. So this triple bracket here would be x to the 6. When you do all parts and tidy it up, I'm going to just sort of speed it up for you. And so that would differentiate to 6x to the 5 minus 24x cubed plus 24x, and then the constants disappear. Good. Now this does in fact kind of factorize as well, and I'm going to write this in a slightly different way. I'm going to write this one and you might be thinking, why is he doing it like that? Why is he writing it in this way? It's basically to show you how the chain rule works. So this session will be approximately an hour. I'm going to get as far as I can with this topic. And if you guys in the chat could just remind me who here has started chain rule before, who has seen this rule, because they might then spot where I'm going with this. If you have seen it, let me know. But basically what the rule is, if you've got a function within a function, so x squared minus 2 is within a cubic function, you essentially differentiate around it and times by the derivative of the inside. So that's what I'm kind of trying to show here in this bit, and I'm going to write this rule explicitly. Now I know from when I've done this with classes before, when they see the rule written in general terms, it looks really confusing, but we're going to do plenty of practice of it. So basically what you might have noticed is that the power of the bracket is a part of the answer. The derivative of the inside is a multiple of the answer. Sorry, is a factor of the answer. And then the actual thing inside the bracket is so if I differentiate around it, what I'll see is I get essentially n times by the derivative of the function times by the original function to the n minus 1. And we're going to work towards this chain rule. So what this does, this is good for all exam boards. What we do is when we've got a function in a function, we differentiate in the normal way, n of the thing, drop the power by 1, but we have to times by the derivative of the inside. So the derivative of this, for example, for this question was 2x. For this one, the derivative would have just been the derivative of x, which was 1. And so we've brought the 2 down and made the power of the bracket 1. So we're going to see this with more examples because this does get quite challenging. And as I said, yeah, this is a chain rule scenario we're looking at. So I'm going to move on and we're going to have a little look at some harder looking examples. And I appreciate that this rule does look really confusing if it's the first time you've seen it. But what we're basically doing, as I said, is bringing the power down to the front, dropping the power by 1, and then timesing it by the derivative of the thing that was inside. So I'm going to do that now for this question and hopefully make more sense of it. And we'll keep referring back to that rule. So let's have a little look at this one from scratch. Cos x, if you're in year 13 and you've learned how to differentiate cos x, as we mentioned earlier, cos x differentiates to minus sine x. So what I'm going to do following this rule is I'm going to bring the power down. So it's going to be 2 times that bracket to the 1. And that is essentially this bit. And then I'm going to times it by the derivative of the thing that's in here. So now I just need to be able to differentiate cos x and e to the x. And they actually differentiate, if you're not sure, to minus sine x, and e to the x differentiates to itself. And that is the answer. And well done if you got that. So I appreciate this is really tricky. And this is, as I said, bringing together lots of year 12 and 13 ideas. But I'm trying to go through this rule carefully because it's actually hard to understand just when you see it written. But when you see a few examples, it hopefully brings it to life, makes it a bit clearer. So that is actually fine, leaving your answer as that. Like in a factorized form, that's actually perfect. That's fine. And even if you put the brackets the other way around, it's still essentially the same multiplication. And you could write that as e to the x minus sine x. That's the same thing. Okay, so what we've done is we've times by the 2 of the thing, dropped the power by 1, and then times by the derivative of the inside. Because this is basically a composite function. There's 2 functions going on. There's something squared, and within that, there's something a lot more complicated than just x. So good question. And that's a really good point. Why does e to the x not go to x e to the x minus 1? That's not like a polynomial. That's not the same as x squared or x cubed. The x is in the power. So when you do the topic of exponentials, you learn that e to the x differentiates to e to the x. It's kind of a crazy cool feature of that function. So that was a good point. And thanks for raising that, whoever did. But as I said at the start, e to the x is one you kind of need to know. And we might see a few more of them today, but it doesn't differentiate like a polynomial. It's a sort of whole different type of function, as is sine and cos. They have their own little rules. But that's great. Great comments coming in, and I'm trying to keep an eye on that as well. But this is good. So this next one, there is a composite function here because it's essentially something being cubed, but it's also something complicated going on inside. So the inside function is this bit. So let's follow this rule again. I'm just going to clear my annotations just so we can kind of see the rule. The 3 is going to come down as a multiplier of the thing. So kind of don't panic about it for now. And we're putting that to the 2. We're dropping the power by 1. So I've kind of done that bit. And then I'm timesing it by the derivative of that inside bit. Okay. And the derivative of that, if you've learned in year 12 how to differentiate, Root x, remember, is the same as x to the half, and that's the same as minus x to the minus 1. So if we differentiate each of those, we're going to get 1 over 2 root x, and we're going to get minus 1 over, oh sorry, no, actually that's going to go to plus x squared. Okay, and that was probably quite tricky, but that is something you've hopefully seen from differentiation in year 12 if you've covered it, how to differentiate something that looks like this. So again, you times by the power half, and you drop it to minus a half as the power. And then the next one, you times by the power minus 1, and you change the power to minus 2. And that's another way of writing that. Okay, so that's lovely. So again, that's fine as the answer. There's nothing wrong with writing that as the answer. So 3 of this thing. And I appreciate you guys following along because there's lots, this got quite complicated quite quickly, but really well done, and do keep asking the questions. I'll do my best to keep checking the chat as well as writing. Lovely. Right, cool. So moving on. This one here, we're going to use the same rule. And again, if you're perhaps in year 12 or you haven't done so much trig in year 13 yet, then you might not have even done the function sec. So sec, cosec, and cot, they are reciprocal trig functions that might be completely new. You might not have met those before, but I'll explain what that is. So sec is 1 over cos x. It's got its own name. It's the reciprocal. It's 1 over cos. And it's the third letter that actually tells you which trig function it relates to. So a lot of people think it's 1 over sine, but it's actually 1 over cos, that one. So 1 over cos is what we're differentiating. And then we've got root e to the x. Okay, so I'm going to just rewrite this. And I do just want to stress, this is not, we've not picked an easy topic to go through. This is tough. So please don't worry if you think, well, this is really quite challenging. Obviously, you can go back over this video. There's a lot of practice questions of this, but do also ask the specific questions if you want to clarify anything. So sec, as I said, is cos x to the minus 1, and you might be able to see how that will become a chain rule in a second. And this is the same as e to the x to the power of a half. Okay, and just if you're getting a little bit confused with the notation, I can write d over dx as the derivative. You don't always have to keep writing dy dx every time. We don't need to introduce y. That means just differentiate it. So I'm differentiating cos x to the minus 1 and e to the x to the half, because a half power means the square root. Can I just check before I carry on and differentiate this, that everyone is actually clear that this is the same thing? So if you didn't know what sec was, then I've written it in there as cos x all to the minus 1. But is everyone happy that the square root is the power of a half? So if I've got the root of e to the x, that is the same as e to the x to the power of a half. Is everyone okay with that? Does that make sense? E to the x to the half is a square root. Yeah, lovely. Okay. So what I'm going to do is carry on and differentiate this. And what we're going to have here is, again, times by the power minus 1 times by the thing that was in there, so cos x to the minus 2. And then that's going to be multiplied by the derivative of cos x, which is minus sine x. Okay, we'll tidy that up in a minute. And then this one, again, it's a chain rule. So you're going to get half e to the x, and then you're going to drop the power by a half, which is, by 1, which is minus a half. And then you're going to times by the thing in there differentiated, which is just e to the x. So as I said, exponentials are a weird one. They differentiate to themselves. So their gradient function, their derivative is themselves. And if you've looked at exponential functions, they are quite cool and quirky. And especially this year of all years, with everything in the news, exponentials and exponential modeling is actually something really important to understand and know what's going on. So their gradient function is really cool. It's actually itself. Here we go. Let's carry on. So well done if you've recognized that. The minus and the minus will become plus. And what we essentially get is sine x times cos squared x, which you can write as this. Cos x all squared is cos squared x. That's great. I'm sorry, no, it was cos x to the minus 2, wasn't it? So that's 1 over cos squared x, which we'll further tidy up in a minute. And then tidying up the powers here, we're going to have a half e to the x, e to the x to the minus a half, which when you times, you add. So this will become sine over cos squared. And this bit here will become a half root e to the x. And that does tidy up. I've noticed some people in the chat have mentioned it. And sine over cos squared is the same as sine over cos times 1 over cos. So very well done if you notice that that becomes tan x sec x. So sec is 1 over cos, and then plus a half root e to the x. So actually by this stage, you had done the differentiation. You had used the chain rule for each bit, but it's just tidying it up from then. And that's what we did there. And it uses trig identities. It obviously uses the knowledge that the reciprocal trig functions have different names, and you can tidy those up. Good, right, let's look at this other one together then. So I appreciate they're still quite tricky, but that's fine. Here we go. So let's rewrite this as a more obvious chain rule. So hopefully, and just check you agree, is everyone happy I could write this as x cubed minus 4x all to the power of minus 1/3. Is everyone happy with that? Yeah? Excellent. Okay. So even if you're struggling a bit with this differentiation, let's be able to manipulate it so it is more clearly a chain rule. So that bit, that is actually just year 12 early on index laws, rewriting stuff that you do it in the first term of year 12 before we even differentiate it. So it is important that you know how to make that look more user friendly and like you can do differentiation on it. Now it's a chain rule. It's some complicated function to the power of minus 1/3. So around that, we're going to times by the minus 1/3, drop the power by 1, times by the derivative of the inside. So let's do that. Let's go through that process, and it's probably nicer than the one we just did. So let's have a little look. So times by the minus 1/3. So you bring that to the front. The whole thing we had, drop the power by 1, and be careful here. So minus 1/3 minus 1 will be minus 4/3. And then we're timesing that by the derivative of x cubed minus 4x. What is the derivative of x cubed minus 4x? Year 12 style, differentiate x cubed minus 4x. What do we get? So if I differentiate x cubed minus 4x, I get 3x squared minus 4. Times by the 3, drop the power by 1, and then x minus 4x just goes to minus 4. So there we go, and we get, that's our final answer. That is basically it. So that was a lot nicer, that one. It didn't involve any complicated trig. It didn't involve any exponentials. It was just a weird looking algebraic one to do. Very good. So hopefully that one was, maybe the second one was slightly easier there. Right. Now, next slide. Be honest, and I can see from the chat already, kind of getting a gist of how people are finding it. Some people are struggling. Not a problem. Just a 1, 2, or 3 on how you feel. Hopefully not super confused, but you can be honest, it's fine. And if some of you have seen it before, maybe it's okay. Maybe it's a little bit easier now, hopefully. But don't worry, this is just, at least for those that are maybe in year 12, an indication of how challenging this is going to get quite quickly in year 13. And that's fine. Okay, got some funny answers coming in there. Lovely. Right. So let's have a little look at the next one. Now this one is a little bit weird, but I feel like it's worth doing these quirky questions because you can go through the motions of practicing the questions you like in the textbook and think, yeah, and convince yourself you're really good at it. And then everyone gets to a mock exam and the topic they thought they were good at, they hit one hard question and it just takes too long. And it's we all know that feeling of when you're in a test and then you suddenly think, how have I stopped knowing the thing I'm good at? And that's why we need to try these nastier questions. So this one here, we want to make it a chain rule. This is going to involve a little bit of manipulation at the start because this is not just a function in a function. It's times by an x squared. And there's different rules for that. So what I'm going to do is I'm going to make this more clearly a function within a function. So the first thing I'd like you to do is just tell me if you can see what I've done, because this is not an obvious trick and it's something that a lot of people won't recognize you could do. So just tell me if you agree that we can write this as y equals the square root of 5x to the 5 minus x to the 4. And you might be thinking immediately, hang on, that's changed completely. What's going on? This isn't obvious. This is just something we need to be careful with. This is kind of like the reverse process of when you simplify surds. So what I've done here is to bring something back into the square root, I square it. So if I times through by x to the 4, I can make this one function under the square root. And it's not a process we ever really do or we think to do, but it actually really helps here. Can everyone see that? Well done if you've got that. It's one of those things you kind of have to see done to then realize, oh, okay, yeah, that could be a thing. But it's not something you ever are necessarily taught, making like a surd look worse or more complicated. But all we've basically done is gone, well, if x squared came out, I could put the square of that, so x to the 4, back in, and then I've got everything in the square root. So it's a cool little trick to be aware of for these quirkier exam questions. So that's just, again, some of these questions, there's a lot of work before you even do the differentiation. And I know from myself when I was, at A-levels, you do all this work and forget to do what the thing asked. Like you could do loads of work before you even differentiate it. But now we can treat it like a chain because we know that we can write that as 5x to the 5 minus x to the 4 to the power of a half. Okay, and now it's a more obvious chain. Now it's like, okay, it's a function inside a slightly more complex function. So what I'm going to do to differentiate it, and I do really want to say well done, guys. I know that we've dived into a really tough topic, and these aren't easy questions. These are like weird versions of questions anyway. So what we're going to do here is we're going to times by the power of a half. So we're going to do the thing we've just been doing of the thing that was in there, and then drop the power by 1. So a half minus 1 is minus a half, and then I'm going to times all of that by the derivative of the bit that was in there. So differentiating 5x to the 5 minus x to the 4 will be 25x to the 4 minus 4x to the 3. Okay, and that doesn't look nice, and we're kind of thinking, okay, that's great, what do I do now? We are pretty much there, but the question just asks something very specific. I'm just checking the chat there. So for those that are still wondering where this bit came from, I times by x to the 4 to put it into the root. So it's a bit like complicating the surd, but just to get everything in the surd, I times by x to the 4 to bring the x squared in there. Right, now I've got the derivative. It's a bit like a year 12 style question in that it's asking for the value of dy dx when x is 2. So now you've found dy dx, that was the hard bit. All you need to do now is sub in 2 for x. So you literally put x in as 2 and evaluate it. Right, and that's a good question. Like, can we simplify that? Do we need to simplify it? No, that is the derivative. And actually, it's better leaving it factorized, because anything you're going to do, trying to expand it or do kind of crazy binomial expansions and things doesn't actually help with anything. That is the derivative. The fact that it looks nasty is because it's A-level maths and you're doing a tricky topic. So we're just going to sub in 2. So let's have a little look. We're going to sub in, so let x equal 2. And we're going to get a half times 5 times 2 to the 5. And obviously do this on your calculator. And something that is worth noting, and you're probably all going to think, well, why didn't he just say this at the start? But you might already be aware. Your calculator, so the newer calculators like the Class Whiz, do actually work it out for you from scratch. So if you wanted to differentiate x squared root 5x minus 1 with x equals 2, you can actually use the button on the calculator underneath on. So for the Class Whiz, it's the one that has the integral symbol, and above it in yellow, it says d dx, and then a yellow box. If you press shift, that will let you evaluate derivatives at a specific value. And you can do the same for integrals, but it's not going to get you 6 marks. It's just really good to be able to check your answers. So the chain rule, a good question there, and we're going to see that as we go. How do we know when to use it? So let me just finish this question off, and I'll explain. But it's basically for functions inside functions. So when you've got a complicated scenario to a power, or a function within another function, that's exactly when we use it. So I'm going to sort of do a clearer definition of it again in a minute. It was just, we were keen to get on to some practice there of that. So that's going to be minus, yeah, I think, tidy that up quicker to speed us on. I think it boils down to 400 minus 32 over, and very well done if you already got this. I think someone in the chat had already whizzed ahead and got the answers, or maybe it was a few of you, but it is absolutely 46 over 3. So very well done if you got that answer. Yeah, you are allowed. That was a good question. Good question. Some really good questions in here. And I know it's not quite GCSE maths. It is a lot harder than that stuff. You could have used the product rule here. And for those that have covered that, that is another way you could have done this question. But you still would have needed the chain rule as well for the root bit. So don't worry if you thought, oh, this should have been a product. But what I was doing is showing you could make this one chain, one thing, where you bring it into the root. So you could have done that. That's not a problem. And also, you are allowed those calculators, yes. So that does help for checking. And I would recommend, that you have that, and you have, because they are allowed in the exam. Okay, so this one now, let's have a little look at this one. So this one here, again, is bringing together some really tricky topics from year 13. This is bringing in a bit of algebraic fractions. And so the first part of the question, it's quite scaffolded, is actually asking you not to differentiate it, to get it into a simplest form. So let's do that. So the way we do this isn't differentiation, this is algebra. So hopefully we can all kind of get on board with this bit, whether we've done the differentiation or not. And basically, just like you would with numbers, we want a common denominator so we can write it as a single fraction. So this needs another 2x minus 1 multiplied by it. So if I times the first fraction by 2x minus 1 over 2x minus 1, I've basically times by 1 in a clever way. But I've got it as an equivalent fraction with a common denominator. Does everyone see what I'm doing there? So what I've essentially done here is I've made it so it's got a common denominator, times in by 1 in a clever way, and then I can write it all as a single fraction. And then the other bit was already had that denominator, so it's just minus 3 over the same thing. So you can write it all as a single fraction. Is that okay? So if I expand maybe the top bit out, I'm going to get 8x squared. Let's whiz through and do this. Minus 6x plus 1 minus 3. Lovely. Good. So this is the first part of the question. And as you can imagine with the A-levels, there'll be like multi-parts, and that even if you struggle to do one bit, it should be like a show that or something where you can still carry on with the question, which is quite good. So it'd be good if we can all get this bit done, and then we'll look to differentiate it. So that will tidy up to 8x squared minus 6x minus 2 over, and I'm going to keep the denominator factorized, because what I'm looking to do when I simplify algebraic fractions is actually cancel bits. So I actually do want it factorized. And now I can refactorize the top. So there's a common factor of 2 that can come out, and I'm going to get, sorry, and well done if you've gone ahead and already got this, that's superb. 4x squared minus 3x minus 1. Hopefully we agree with that. Do stop me or comment if you're not sure or you don't agree. I'm not trying to make any intentional mistakes like maths teachers sometimes do. But here we go. The 2's will cancel and the top will actually factorize. And a good little technique for, because you obviously want to show this working, for when it factorizes, is actually use the denominator to help you look for what might be the brackets. If you struggle factorizing quadratics, because the chances are it's going to cancel down if they've asked you to do it. So there will be a common factor with the bottom, and you've already got that factorized. So then that's going to boil down to 4x plus 1 over 2x minus 1. Now, sorry, I'm just going to read your comments to check I'm keeping up with this. Thanks for that. Why is the 2x minus 1? Okay, because the original thing, this was the common denominator, we needed to times by a 2x minus 1 over here. So I could write it as one single fraction, and then I could simplify it. So you could write 2x minus 1, x minus 1 the other way around, like a times b or b times a, but it was always a factor of the denominator, okay? And this is your answer. So this is your 4 mark, and all that was really was algebra. That was algebraic fractions. So it's kind of a GCSE recap, but it was still involved and still took a bit of work. Good questions, guys. I really appreciate the comments. This is great. Here we go. So now this one, it says, given that the function we're looking at is this thing, which we just simplified, minus 2, show that f of x is this. So this is just more algebra on the kind of topic we were doing. So let me just do that. So basically, I knew that all of this stuff here, sorry, it's going to move on. All of this stuff can now be rewritten as 4x plus 1. And notice this is only 2 marks. So this is about spotting stuff, because I've just done that in part A. And then I'm minusing 2. And I'm trying to make this look like this. Okay, so the way I'm going to do that, similar sort of thing again, is think, well, how do I get the minus 2 so that I put it all as a single fraction? So what we've got here is we're going, well, the first bit is fine. It's 4x plus 1 over 2x minus 1. And hopefully you're happy that that's the same as minusing 2 lots of 2x minus 1 over 2x minus 1. Because that's just times it by 1 in a clever way. So it's like 2 is the same as like 10 fifths. So it's like the thing over the thing times 2. So what I can do as a single fraction is write 2x minus 1, and on the top 4x plus 1 minus 2 lots of 2x minus 1. And if I now expand that and tidy it up, I get 4x minus 1 minus 4x plus 2. Sorry, it was plus 1, wasn't it? Well done. And then the denominator was 2x minus 1. And then that all tidies up. The 4x's cancel. And I get 3 over 2x minus 1. And again, this question can kind of verify that your previous answer was right, because then you do end up here. Okay, now it says differentiate it. So now it's a chain rule. So let's look at this as a chain. So for part B, we've just done that. For part C, hence differentiate. And again, remember, even if you struggled with part B, it doesn't mean you can't differentiate it, because you can go, right, I messed up A and B, but I do know how to differentiate that. So I can just use the result that I should have got to and just do differentiation on it. Okay. Yeah, there's lots of different things they could bring in here. I'm just reading the comments. Sorry, I just missed that. They could ask you loads. This topic then starts to branch out and touch lots of different other subtopics. So you're right. This question could be lots of parts. It could be all overlapped with different ideas. So here we've got, let's just think about this function is 3 times 2x minus 1 to the minus 1. Does everyone agree with that? That's more of a user-friendly form for differentiation. Is everyone okay with that? Yeah, I think some people have written that in. That's great. Well done. So if I now want the derivative of it, so remember, if we're using, we're not using function notations, we use d dx, dy dx. If we're using f of x, then we use f dash to mean the derivative. Lovely. So what we're going to do here is times by the power, which is minus 1. So we're going to get minus 3 of that thing, drop the power by 1, and then times by the derivative of the inside, which is 2. So I end up with minus 6, 2x minus 1 to the minus 2, which is actually the same as minus 6 over 2x minus 1 squared. Okay. Oh, good question. That dash means that's notation for the derivative. It's the same as saying d dx. So that's not the function, that's the derivative of the function. And that's what it says here. So they want us to differentiate it, which we just did. And then they want us to find the derivative when x is 2. So then we literally just sub in minus 6 over 2 times 2 minus 1 all squared. And I believe we get minus 2/3. Okay, sorry, I've really used the page in a weird way there, but hopefully that's nice and clear. Lovely. Is that okay, guys? So yes, we're going to quickly recap the chain rule. I'm conscious of the time because we've got loads of content on here, but we'll carry on and see how we get on. So just to basically go overview of the chain rule, because as I said, it's a big one and there's overlaps with lots of different ideas. So basically, if you've got an outside function, this is the more general version of it, which is f of x. So f of something, f of another function, then it's a function of a function. It's what we call a composite function. What we do is we differentiate the outside of the thing and times by the derivative of what's in it. Okay, so I'm going to show you for these here. So if I asked you to differentiate sine x to the 10, to the power of 10, the overarching function, the f function, is something to the 10, or something to the n in this case. So the f function is x to the n. So the way that differentiates, as you know, is nx to the n minus 1. The inside function is sine x, and you know that differentiates, or for those that have covered this, that differentiates to cos x. Okay, so now putting it into that rule, differentiating around what's going on, we're going to get n sine x, because that was the thing, to the n minus 1 times by cos x. So it's the same process we've been doing, but now it's all sorts of weird scenarios going on, all different functions. So yeah, so this is a rule. This chain rule doesn't just apply to those ones that look like algebra with x's and polynomials and similar, and just things, brackets to a power. It applies to logs, it applies to exponentials, it applies to trig. It's a very general rule, but applying it, we've got to be very careful. So we've got to kind of think, what's the overall function and what's the innermost function? What's the outside function? What's the f function? What's the function that's happening within that? So here, overall, it's an exponential, but instead of just being to the x, it's to the ax plus b. So e to the something goes to e to the something, but then I have to times by the derivative of the inside function, and the derivative of ax plus b is a. So it's going to gain that number in the front. So if I said differentiate e to the 5x plus 2, it will become 5e to the 5x plus 2. And in a very similar way, for sine, the outside function is sine, which differentiates to cos, but the inside function is ax plus b, which differentiates to a. So this will become a cos of the thing. Okay, so this is actually a chain rule question as well. So let's do another one. Here we've got cos ax plus b. So the outside function is cos, which differentiates to minus sine. But the inside function is ax plus b, which differentiates to a. So it becomes minus a sine. This is A2. This is year 13 content. Yeah. So we've built on some year 12 ideas, but this is very much, very involved differentiation from year 13 that you do see quite quickly and is really important for the rest of the course. So that's great. Hopefully we've kind of followed that and can see how that relates to the same rule. I'll do a couple more and then I might skip on a little bit. So let's have a little look. So this one again, let's really carefully do the chain rule on each of these. So let's have a little look. What we've got, the outside function, if I lay it out in that way that we just did, the overarching function is cos. So that differentiated is minus sine. So the whole thing is going to become a minus sine. Inside the cos function, because it's composite, is 3x cubed minus 2. So now year 12 style, can you tell me what that differentiates to? What does 3x cubed minus 2 differentiate to? The derivative of the inside one. So what does 3x cubed minus 2 differentiate to? Lovely, 9x squared, well done. Cool. So now putting that all together for this rule, the derivative is going to become, so we're going to have minus sine of that thing, because cos goes to minus sine. So that's the overall effect. And I'm timesing it by 9x squared. So it'd be minus 9x squared sine 3x cubed minus 2. That is the derivative. And that was a chain rule question. So this one here, this is quite involved, but I think we should work through it because we're kind of building to this. So again, let's separate it in a really similar way. What's the overarching function? What's the outside function? What's the function within it? And what do they both differentiate to? Okay. So I'll talk about other topics that are coming up and stuff in a bit. But as I said, this is pretty full on for today. So we're going to see how far we get. Okay. So the overarching function is it's an exponential. It's an e to the x. So that's going to differentiate to an e to the x. E to something differentiates to an e to something. And the inside function is a bit more involved. It's x squared minus, and I'm going to write it as x to the power of minus a half, which hopefully we're familiar with. That will differentiate to 2x minus, oh, actually, no, I'm going to times it by the power. So plus a half x to the minus 3 over 2. Well done. And then we're going to now put it into the chain rule. So what we're going to have here is it's going to be this, the derivative of the inside one, times by the overall thing and what it differentiates to. So it's going to be, the overarching function will be e to the x squared minus, but that is going to be multiplied by the derivative here. Okay, so they're starting to look really nasty, but you can kind of get a sense of where this is going. Oh, that's really nice to hear. This is tough. Like even when this has been explained to you a few times, you've done it in class, you've done a bit of practice. It only takes one quirky example, one weird question where it can confuse you and you think, oh, hang on, I've forgotten how to do the general thing now. So this does take a lot of practice, but I think the reason we're doing this and the reason we think this is a really important class to look at is because when you move on with the pure in year 13 and you do integration, you have to be so familiar with the differentiation, and it's crucial that you practice this and you don't think, oh, that's just something I can't do, because it will affect other stuff. But that's great to hear. So what we'll do, I'm just kind of conscious of the time, might do this one and then maybe skip on a little bit, and that'd be good. And I'll talk about, other resources and what we can do to practice this further. So let's do this one, as I said. and go through it together. So again, let's break this down and think about what the overall function is. So overarching thing is there's a sine of something. Okay, the derivative of that, sine differentiates to cos. And again, you don't really see this till year 13, but well done if you're following along and you've kind of picked up on that. And then the inside function is obviously this bit, which is like the nasty looking bit for this question, which you can think of as e to the minus x plus 4x all to the half. And that's great. And then differentiating that is going to go to, so that in itself is a chain, because to differentiate that, you're going to go a half e to the minus x plus 4x to the minus half times by, and that will be minus e to the minus x plus 4 will be the derivative of this. And so what we get is we get this whole thing is just the derivative of that nasty inside bit. So now, putting it all together, the answer is going to be cos of the thing times by all of this. So it's going to be cos of what was originally in there multiplied, and you're absolutely right if you think, well, that looks horrible. But again, it just comes with a bit of practice, and this was a nasty question, but hopefully we can see where all the different bits have come from. Yeah, so that was quite involved, but well done if you got that and you followed that, and you could sort of tidy it up, bring the half to the front, put the minus power on the denominator, but it doesn't look much nicer. Cool, so how are we feeling? Maybe not thinking about the worst ones in mind there, but just overall with the concept of the chain rule of differentiate the outside times by the thing, and of the thing, and then times by the derivative of the inside. So on the whole, this is just something that builds and builds and gets more and more involved, but actually the actual principle is for composite functions, functions within functions, we use the chain rule. Okay, cool. So there are a few more exam style questions, which I think we'll struggle to get through now, but as I said, I'm going to explain resources and where you can look, and also how you can best prepare for this. Overall, what we've looked at today is differentiating powers of brackets, and actually even with negative and fractional powers, how we can apply the chain rule. That's lovely. Thanks for the comments, guys, and well done for everyone for being involved. I know it wasn't easy, and it's not easy to write maths in a chat box, so I appreciate that as well. But we also used it for trig and exponential functions, which if you're in year 12, you may not have even met those yet. So that was really well done keeping up with that. What I'd like to do, obviously keep the questions coming in the chat. I'd like to just quickly talk to you about SnapRevise and obviously the resources we have on the platform, and also how you can just generally prepare for your A-levels. I know this has been a challenging year, and a lot of stuff has had to be done independently, so you might not have had as much contact time with a teacher in school as you would normally. But what I'm going to do is I'm just going to quickly share a different screen here. So can you all see this? This is the SnapRevise website. Hopefully you can see that okay. And basically how it works, you may have seen this before, but essentially what we have is the different courses are broken down, lots of diagnostic quizzes, which are quick and easy to do with every topic sort of in there for year 12 and 13, loads of revision materials. So I'll just show you, for example, if we take proof, you can start a quick quiz that works out what you know. I'm obviously guessing this and not thinking about it, but you could do it properly, and it will kind of diagnose how you're finding the topics and actually pinpoint what the problem is, because a lot of the time it's hard for you to even say, oh, it's this part of the topic I don't like, or you might think it's one thing that's causing you an issue, and actually that's not the problem. It's the step before. It's how you write your answer or something. So these quizzes on here will allow you to work through the topics and do a sort of quick 10-question quiz or sort of quick diagnostic quiz. And then with your results, it will work out what you know and what you don't know. And then it will take you to a video, which can actually be jumped. You can jump to kind of the key bits you struggled with by clicking on those parts and those topics, those little subtopics. And then alongside that, we have lots of questions. You can speak to the tutors who can answer your specific questions. And also, it will tell you the exact bit in the specification where this comes from for your board. There's an exam pack. There's really nice, clear revision guides. So, for example, if you answer this question, the solution is laid out perfectly clearly, how the marks are broken down, and examiner report information and guidance, which is brilliant. So really easy to follow, and you can pitch it at different levels. The revision guide is just really nice and clear notes that you can print off and use for revision for different topics as you go, which is always great. And then on top of that, so if I just go back, so let's have a little look, view my courses. So for example, for maths, we also have web classes every week. So I do a year 12 and year 13 web class followed by a drop-in. So we'll follow a schedule that basically parallels what you'll be doing in school generally. So it'll go through pure mechanics and stats. So for example, here are some upcoming ones. Tomorrow I have a session on integration for year 12, followed by a drop-in. So if you're struggling with homework or you've got a test coming up, you can email the questions in or ask me live in the drop-in to go through a question you're struggling with, and we'll do that there. And then on Wednesdays, we have year 13, same scenario again. So there's loads of web classes happening all the time, as well as drop-ins that you can join if you're part of the sort of SnapRevise package. There's loads there. So it's quite interactive and lots of kind of contact time and opportunities to go through some of these really difficult topics. So if you've enjoyed that today and that's worked well for you, it might be something to consider. Obviously, so I'll just stop sharing that for a second. Resourcing yourself and being prepared for the A-level is really important. And a lot of people are aware of, brilliant websites for maths. There's no sort of shortage of content online. But something to just bear in mind specifically is that obviously with the new A-level, there have been changes. So the old A-level exam board, you might find on some websites, it's called C1, C2, S1, and it's geared up for the old A-level. And that's fine, but there has been a change in 2017 and all the stuff on SnapRevise is kind of geared up for the new A-level and all the changes that have been made. And so it's a lot more seamless and works a lot better for the current A-level that's in place. And it's constantly being tweaked and updated. So works really well. I'm just going to try and quickly get us back to the PowerPoint there and basically wrap this up. But do keep the questions coming back in. I'm going to try and keep an eye on that. So if I just finally share this last little bit with you. Thanks again to everyone for taking part so well. I know it's Sunday and we're getting into winter now. It's been a strange old year, but really well done. Hopefully you can all see that. Back to my PowerPoint. Brilliant. So just to kind of conclude, SnapRevise, there's loads coming up, but on YouTube, we do have these web classes as well. That's a really lovely comment. Thanks for that. You're making my head big here. And we've got loads coming up, so you can set reminders for that. And, obviously we're cycling through the different subjects. But as I said, there's loads going on all the time on the platform. So on SnapRevise, if you're signed up for the package, there's web classes all the time, drop-ins. So feel free to look into that. And yeah, I think, as I said, there's lots of resources online, but it is good to be able to speak it through with someone and pinpoint the questions. So try and really narrow down where the issues are. There's a code here. So for £10 off, CR10 expires at midnight tonight. That will give you £10 off your first month if you're interested in signing up for SnapRevise. And as I said, if you took the picture and put it in your story on Instagram, and there's a free giveaway for an account as well today. Right, I'll stop sharing that. Just going to check the chat in case I've missed anything there. But I think that's been posted in there. One of my colleagues has put the link I'm not like doing this with my mind or something. There is someone else doing this for me, which is great. Yes, lovely. And yeah, really, really well done. I'm just trying to check if I've missed any questions. Lovely. Oh, that's great to hear. As I said, there's more web classes coming up, so feel free to set a reminder on YouTube and also look at what there is on offer for SnapRevise if you want to try it out. But good luck. I know it's a difficult term, whether you're in year 12, 13, or perhaps year 11, as some people are. So keep going, keep working hard, and yeah, hopefully see you at one of these web classes soon. Thanks, guys. Take care and enjoy the rest of your weekend. Let's get into the end now. Well done. Thanks, guys.